Hey everyone, welcome back. This is our last review video of Calc 1 material. So in this video I'd like to talk about u-substitution method for integration and maybe take a slightly different point of view on this from how you might have learned it. So first of all, before we actually tackle this problem, let's do a little general discussion here. If you want to evaluate a definite integral from a to b, f of x dx, then geometrically, what are you trying to do? Well, you are trying to compute, I'll draw this down here actually. You're trying to compute an integral, right? You're trying to compute the area underneath a curve from a to b. I'll just draw a positive one. All right, and you want to compute this area. So in the way that you do it, generally, by Riemann sum methods, is that you chop up this, I won't draw the boxes, but you chop up the region into these rectangles, okay? Now, we have a fundamental theorem of calculus which tells us that this can be computed, if we know an antiderivative, this can be computed as f of b minus f of a by the evaluation theorem, very simply, right? So in other words, if you know an antiderivative here, then you can compute this. And yeah, so that's the easiest way. But when you look at this problem, you see that you don't really have, you probably don't know the antiderivative of this function the way that it is right now, right? And so instead, what you want to try to do is change the coordinates. Now, what are the coordinates here? You want to try to change the x variable into a u variable. So you want to change, but you don't want to change the picture, right? You don't want to change the picture too much. So in general, what are you going to do? You're going to leave the y variable the same. That's the output of the function. And you're going to leave the shape of the graph pretty much the same, right? So you've got now your function, this is the graph of y equals f. In this case, it's y equals f of x. Over here, this is going to be the graph of y equals f of some other variable. We call it u, so y equals f of u. And now this is our new coordinate system down here. It's going to be u instead of x, right? So how is it going to work? Well, it's going to take a, and it's going to map a over here to some other number. Let's call it c, but that's going to be the left endpoint, right? And then it's also the other rule, obviously, is that it's got to take this number b, and it's got to map b over here to, let's call it d, and that's going to be the other endpoint. And in between, it's got to map all these vertical lines. So it's got to map this entire partition that we found right here. So all these partition points have to get mapped over in a one-to-one way, right? So they have to get mapped one-to-one. That means that for every one of these, you get one over here. But the way that it's done is not necessarily going to be linear, right? So it could be some of these are grouped closer together and the other ones are not as they go over here. All right, so what you've done now is you've changed your coordinate system. You've got the exact same shape, right? So it's going to have the same area. You've got the same shape, but the other thing that you've done, though, is you've either stretched out, possibly. It could be stretched out more. Maybe the scale is bigger here, or smaller, or squished. So you've got a couple things going on. You're changing the interval from a to b to an interval from c to d. Might not be the same length, right? It might not be the same length. And you're possibly, these cannot change the order that they're in, right? They still go in this direction. They're still counting in this direction, right? But they maybe are closer together or spread out more. But when you compute the areas have to add up to the same as this one, right? Because you haven't changed the shape, the general shape of this thing. All right, so this is a very philosophical picture that I've drawn. It's kind of a mess, the picture. But the whole point is that actually what you're doing when you do a u-substitution is what you're actually doing is you're finding a map, a function, a change of coordinates, right? You're finding a function, u equals u of x. So it takes in the x values, spits out the u values, right? And it does it in a way that is one-to-one. So remember, one-to-one means that for every output over here, it only comes from one input. And it's also got to obey some other rules, but we'll just stick with this. It's one-to-one. And so what that means then is that this is by the inverse function theorem, which you should review if you haven't heard of the inverse function theorem recently. But by the inverse function theorem, this means that u inverse exists, right? So this has this has an inverse function. By the way, we also want this u to be differentiable, right? It has to be differentiable because this is calculus, and we want to make sure that this change is smooth in some sense, that the change of coordinates is smooth. And so what we learned then, the inverse function theorem, what does it tell us, right? It says that u inverse exists. So what does that mean? That means that x is equal to u inverse. So what? Yeah, I mean x is equal, so you would rearrange it. It's kind of weird when you have all the same symbols, so I won't even write it that way. But here's what it really means, right? Is that if you have du dx, that this can be inverted, right? And so you can write this as 1 over dx du, and vice versa. All right, so let's see how this plays into our integral here. And in reality, I'm going to introduce some more symbols here. So in reality, what we've done is we've taken this integral. So the integral from a to b of f of x dx. Now, whenever you integrate, you have to integrate a differential. So this is, you could write this as df of x, right? So the differential of f with respect to x. Well, this must be the same. So df of x. This must be the same by this argument up here as the integral from c to d of df as a function of u. Okay, but what are these two? Well, on one hand, so what are the differentials, right? So on one hand, df is equal to f prime of x dx, so the derivative of f with respect to x, so I'll write it in those terms, df dx dx, right? That's the differential. So from Calc 1, that's the differential of f with respect to x. But on the other hand, df is also equal to, and the reason I wrote it this way is because I don't want to use the prime to mean two different things. It's also equal to df du, right? It's equal to the same thing here. But based on what we just computed in the previous example, we can apply the chain rule. We can apply the chain rule to this one, right? So we can write this. The chain rule says that since u depends on x, this whole thing can be written as df dx times dx du times du. Okay? And then look at up here, what do we have? Well, dx du is just 1 over du dx. Right? So really what I should probably do is write it up here. So this one is then going to be df du times du dx times dx. This right here is going to come out of our change of coordinates, right? Our change of variables. So this whole thing is du. This just becomes du. And when you compare this with this, now you see exactly why you have to be careful of everything, of all these terms when you actually compute. All right, so let's actually compute with this. Go back to our example now. We want to actually compute with this. So we don't know the antiderivative of this just by looking at it. We can actually do something before we do anything else. We can see that there's a 3 here that can be factored out, right? So we can write this as 1/3 integral from 1 to 4 x plus 5 over x squared plus 10x dx. And now whenever, if you don't know, so if you can't see that this is the antiderivative of something, whenever you try to make a u-sub, you usually try to pick the u to be in some sense the more complicated part of the thing. You don't want to pick the whole thing. So I'm going to pick the u to just be the bottom, the denominator of this fraction. And if this is true, right, then u, so we're going to put our u equal to x squared plus 10x. So there's our u as a function of x. Now immediately, the first thing that you have to do is you have to compute the du, right? And this is exactly because, if we go back to the previous page, so I kind of fumbled through this, but that's exactly because of this, right? We have to get our differential in terms of du. So we have to find the du and make sure that we have all the parts and that we can make this one-to-one substitution to actually compute our integral. And so we go back here, we compute du. Well, remember, du is the derivative of u, of our formula for u with respect to x. So once we've chosen u, we don't get to choose the u. We have to compute it, right? And for this function, it's going to be 2x plus 10, right? Derivative of x squared plus 10x is 2x plus 10 dx, which for this example, as we start to compare, we see we can factor out the 2, and we can write this as x plus 5 dx. Okay? So this, by the way, is good, right? Because we have these parts in our original integral, x plus 5 dx. We do not have the 2, right? So now you have two choices. One way to approach this is you can take the 2 and you can just put it there, right? And it just seems wrong. It sounds wrong when you say it, right? Like you can't just put a 2 there. Well, since it's a constant, you can put the 2 on the inside and divide it out on the outside. All right, so this is a product now. So multiply by a half on the outside, 2 on the inside. Those cancel out. The other way that you can approach this is you can just take this 2. You don't want it on the right-hand side, right? Because all you've got is x plus 5 dx in your integral. So just get rid of it, right? Move it over to the other side. Well, what's it become? It becomes 1/2 du. So this whole, everything that's boxed in red would become 1/2 du. Or if you put the 2 in the first place, then the 2 times x plus 5 dx, this whole piece right here, would become du. All right, so once you've done this, now your integral becomes, I'm going to leave this all out here. So our integral is now, so integral from 1 to 4, x plus 5 over 3x squared plus 30x dx. This integral is now 1/6. You have to multiply these times the integral of, wait a minute, don't slip up here. We have to compute these new limits, right? We have to see what happens to the limits. But what's left in here, in the integral itself, is a u downstairs and a du upstairs, right? So this is all just du over u. Or another way to write this is that it is 1/6 integral. Boundaries are still needed here, but 1 over u du. That one should be one that we just know by heart, right? Before we write it down and compute it, let's make sure we change our limits, right? So we have to plug in the boundaries into u and see what happens to them. So u of 4 is going to be our new upper bound. When you plug in 4 to this formula, you get 16 plus 40, or 56. U of 1, the lower bound, becomes what? 1 plus 10, so 11. And so our new boundaries of our integral with respect to u are from 11 to 56. Okay, and once we've done this, now we don't have to go back to x at all. So we've made our substitution. We now have to compute. So this becomes 1/6 times the antiderivative of 1 over u. That's the natural log of the absolute value of u. And fundamental theorem of calculus says we can just write down that antiderivative, plug in these boundaries, and then subtract, right? So this becomes 1/6 natural log of 56 minus natural log of 11, which is, of course, equal to the natural log of the ratio, right? So it's 1/6 natural log of 56 over 11. And there you go. That's your integral, definite integral, computed by u-substitution. I took kind of the long way here just to kind of describe the importance of what the u-substitution is doing as it's actually changing the coordinates. All right. But what do you really need to do? Well, when you make your choice of u, you automatically compute du every time. And when you have limits of integration, you make the change here, almost always. You don't have to do this every time, but you make the change here so that when you get your answer down here, you are done.